because it eliminates the parasitic inductance between the MOSFET and the flyback diode. The second objective we put forth in BP1 was to create novel edge terminations for higher voltage devices, 3.3 kV and 4.5 kV devices, and again the goal was to reduce chip area and cost in sync with what Power America expects. So I'll first talk about the JBS FET. The cross sections of the MOSFET and JBS FET are shown on this slide. The upper one is, of course, the MOSFET. It's a pretty standard cross section with source region, channel region, JFET region at the top. Of course, the drain is at the bottom of the wafer or bottom of the device. Our typical design has a cell pitch of 11 microns, and we have done a lot of work on numerical simulation of the structure, and we get approximately 7 milliohm centimeters squared. The resistance is very strongly dependent on channel mobility in these devices, rated at 1.2 kV, as is well known. So one of the challenges for us was to create a process by which we can also obtain reasonably good mobilities, which are in, I could say, similar to those obtained in commercial devices by many companies.
We're waiting for the fan on the TV so we can get the TV turned down.
Okay, the second device structure shown at the bottom, it's called the JBS FET, the one we proposed. In the JBS FET, we are integrating the diode into the MOSFET. It is possible to use the body diode of the MOSFET instead, but as you might be familiar, the body diode has a high VF because of the large band gap of silicon carbide. In addition, it is known that the on-state characteristics of body diodes are not stable, and if you use the body diode, people have also reported instability in the MOSFET characteristics. So you can circumvent all these problems by integrating a Schottky contact into the cell structure. If you use a Schottky contact by itself, one of the problems we encounter in silicon carbide is that you get very high leakage currents because of barrier lowering and tunneling effects. So you can mitigate those problems by using the JBS junction barrier Schottky concept. This is the concept that's already been used to make the commercial JBS diodes or Schottky diodes that are available from numerous companies. In the MOSFET structure, we create the JBS structure by using the P body region and the P plus source contact to buffer the Schottky from high electric fields. So with this approach, the cell pitch gets larger, which makes the RDS on slightly higher, but the advantages are that we have the integrated diode as explained in the previous chart. So there are various ways in which you can do this integration, and then we can analyze the amount of area savings that we can achieve by this approach. Three of these are shown here, and so in what was done previously, there was a separate MOSFET and a separate JBS diode, and we can calculate out the area of these devices for a certain current rating, approximately 5 to 10 amps, and the area worked out to be 0.0707. The first approach, whose cross-section I showed you in the previous chart, we end up with a much smaller area of 0.041, so you can see a substantial savings. There are two other approaches that are shown on this chart as JBS FET 2 and 3. Here, the JBS diode is not put into the cell structure, but is instead created at discrete parts of the chip. So if you take these various designs and compare them, then we find that we can get as much as a 40% reduction in silicon carbide area by integrating the diode with the MOSFET. And of course, you get the other benefits of eliminating one package to reduce cost, as well as getting rid of any parasitic inductances. So this is a very promising approach to reducing cost, which is the mission of Power America, and hopefully also increasing the attractiveness of these silicon carbide components in applications. I'm sure you're familiar that almost all applications need a flyback diode with the MOSFET, for example, inverters for solar applications or motor drives. The next chart shows the mass design that we prepared in BP1. It has numerous devices to be able to compare performance. So we have PIN diodes, Schottky diodes, and JBS diodes. In addition, we have MOSFETs with various designs, and then we have our JBS FETs. The devices are all requiring good edge terminations. At that time, we thought the floating field ring termination might be the best option, so most of the devices have floating field rings, FFRs. We also have proposed a improved edge termination called MFZ JTE for multiple floating zone JTE. So we have also made devices with this termination. The process required 10 math steps. This is a process that was scrubbed by Power America. Math design was also scrubbed, meaning reviewed for several months to make sure it's all going to work well. So we greatly appreciate the support of X-FAB to check everything we've proposed to make sure it'll work when they fabricate the wafer. The process was successfully run, and you can see a wafer here with fabricated devices. The next chart shows that it takes about 215 steps to manufacture these devices in the production facility. And in this first lot with the first mass step, it took about 14 weeks for us to complete the process. Again, all this work was done at X-FAB, and we greatly appreciate the support given by all the people at X-FAB to make this successful. Here's some measured data on the wafers, and the exciting thing for us was our designs worked extremely well, and that's a really big accomplishment for running something for the first time with a new mass set and a new process. So we're very pleased with the results. So let me show you the results on our inversion mode MOSFET. These have an active area of 4.5 millimeters squared. And here we are showing you data on threshold voltage measured at two conditions. And these are very reasonable threshold voltages of 3.6 volts, for example. So the left-hand side chart on this shows the linear scale for the drain current, and the right-hand side shows the log scale. And so these are very good transfer characteristics. In terms of the channel, we can measure the mobility by making special test structures. We call them FATFETs. Some of you who make devices would know about this. So these are lateral devices where we can extract information about the channel exclusively. This chart shows on the blue line the extracted field effect mobility, which decides the resistance of the channel. And you can see from the right-hand side axis that we're getting a peak value of 12 centimeters squared per volt second at a gate bias of 25 volts and about 10 at a bias of 20 volts. Now, in many efforts to make good channel mobility, it is found that the channel mobility peaks at the threshold and then goes down rapidly at the point of gate bias in the on-state. And the on-state gate bias is nominally in the 20 to 25 volt range. So we prefer to have a mobility that peaks at that kind of voltage so that we get good on resistance in our devices. So here's the output characteristics at small voltages to show you the output characteristics as well as the on resistance. So the inversion mode MOSFETs were designed with two channel lengths, more than two, but these two are shown here, one with a channel length of 0.8 micron and the other with a channel length of 0.5 micron, and both were fully functional. The RDS on is reduced by reducing the channel length because the channel contributes a large fraction of the total on resistance. So by going from 0.8 to 0.5 microns, the specific on resistance was reduced from 13.5 to 11.3. We also had good success with our JBS FETs. The output characteristics of the JBS FET are shown on the left-hand side. This is one of the multiple designs that we had on that chip. As you can see from the left-hand side, it functions just like a MOSFET. The specific on resistance is larger because some of the area is taken up by the JBS diode. So for that particular design, the specific resistance is 20 milliohm centimeters squared. In the third quadrant, you can see on the right-hand side that the Schottky diode is kicking in the JBS FET, and that, of course, does not happen for the MOSFET. So for the two MOSFET lines marked MOSFET VG0 and MOSFET VG-5, we're carrying the current through the body diode. And this is obvious from the graph that it has very high VF. In contrast, the JBS FET has a low knee voltage because it's a Schottky contact, and we can get 5 amps with a voltage of only 2 volts. So this indicates that the Schottky diode or JBS diode is clamping the body diode, and the body diode will not conduct in these devices, making them very stable. In terms of breakdown voltage, we have, of course, measured various devices, and you can see on this graph that the breakdown voltage does depend on the structure and the edge termination. If you look at the graphs which are in the middle, where the breakdown voltage is approximately 800 to 900 volts, there's a cluster of devices marked MOSFET short channel, MOSFET with FFR, JBS FET with FFR, and PIN with FFR. All of these show similar breakdown characteristics, so we associate that with the particular edge termination we're using because they all had the same FFR termination. In contrast, if you change the termination to the MFZJTE, then the breakdown voltage improves considerably, and we can meet our design target of 1200 volts. So it is important that we use the MFZJTE termination. The 40 field ring termination we found did not work as well as the MFZJTE. The fact that the PIN diode has the same breakdown voltage as the MOSFETs indicates that it is the termination that's limiting the performance. All right, so our major accomplishments in BP1 were that with just one mass design and one process lot, we were successful in building our MOSFETs and JBS FETs at X-FAB in their production facility. There were no significant barriers to success, and so we felt that this result set up a foundation for Power America to create a foundry process that could be accessed by people who are members of Power America. So this is what we might call an open domain process. Turning to the other project that we did in BP1, these are edge terminations of reduced size for 3.3 kV and 4.5 kV devices, and we proposed numerous designs, FFRs, JTE, MFZJTE, ring-assisted JTE, and then we have been creating this unique bevel termination at NC State with great success, so we also proposed those. A mass design was done to fabricate these devices with various PIN diodes and even some JBS FETs and Schottky diodes. Again, this is a project to look at edge terminations, so we're not making MOSFETs here, we're focusing on the edge terminations. So this process required only 7 masks and was successfully done, again, at X-FAB with 1 process lot and 1 mask design. The wafer is shown on that chart. Since the number of process steps are much less for making diodes, we were able to finish this, or X-FAB was able to complete this in 9 weeks. So here's some results on 3.3 kV wafers. We have similar results on 4.5 kV wafers. The difference between the two is, of course, the epi layer is lower doped and thicker for the 4.5 kV wafers. So I'm only going to show you the 3.3 kV results. You can see here that as we change the edge termination from 30 rings to 40 rings, the breakdown voltage increases from about 2,000 volts to 3,000 volts, but that is still not sufficient. By going to MFZJTE with 60 micron width, we're able to hit our target of at least 3.3 kV. The leakage current is usually spec'd at 100 microamps, which is 10 to the minus 4 on this graph. In addition, we have a termination we call the hybrid JTE. This is slightly wider than the MFZJTE, but shorter than the 40 ring termination. And this is an excellent termination that gives us breakdown voltages as high as 4,000 volts. So this chart compares the terminations from the point of view of space on the edge of the chip. I don't want to spend a lot of time going through the details here. Just want to mention that with the MFZ and hybrid JTE, the breakdown voltages are much better than for the FFR, and we can hit up to 4,000 volts with the hybrid JTE. The chip area is reduced by up to 25% for this small size device, about a 5 to 10 amp device in terms of the active area. The edge termination width itself is reduced as much as 3.6x by using these improved terminations compared to the FFR. One interesting result that we achieved is that our JBS diodes made in this process also had excellent characteristics in the on state. You can see here the IV characteristics. The knee for the JBS diode is at about 1.3 volts compared to 3 volts, of course, for the PIN diode. And in terms of the on characteristics, at a current density of 50 amps per centimeter squared, the VF is only 2 volts, which is excellent for a 3.3 kV JBS diode. So our major accomplishments in BP1 were that we were able to successfully build 3.3 kV diodes with one mass design and process, and demonstrate that a substantial space can be saved on the edge of the chip, which of course translates to lower cost, which is our major goal in PowerAmerica, to reduce the cost of silicon carbide technology. So in conclusion, we ended up creating a foundry process at X-FAB, but this was not qualified, meaning that it had only been run once. So in BP2, we proposed two goals. The first was to qualify the process. We are not qualifying the devices, we are qualifying a process, by which we mean we want to show that the process has good parametric distribution and is reproducible over several lots. If we were successful in doing this, it creates the opportunity to have an open domain process for PowerAmerica, which encourages fabless companies to get involved in this technology. In addition, it creates a licensing opportunity for PowerAmerica for future sustainability. We also proposed in BP2 to create innovative power MOSFETs, 1.2 kV MOSFETs, which are designed specifically for higher frequency operation. Most often, power MOSFETs are optimized for RDS-on. What we wanted to do is to particularly optimize for high frequency operation, because the big merit of silicon carbide devices in applications is that they can work at higher frequencies than silicon IGBTs. So it makes sense to optimize the performance of the silicon carbide device from that standpoint. So I've defined a high frequency figure of merit to allow us to do this optimization. It is the product of R-on, which is a measure of conduction loss, and QGD, the gate charge during the plateau, which is a measure of switching losses. So by taking the product of these two parameters, we get a product that is independent of the area of the device and is a measure of the technology and design. So this becomes very useful in comparing structures, not only that you do in research or development, but you can even compare your devices to any product available in the market by using the R-on and QGD of those products. So our goal was to optimize the design by optimizing our planar MOSFET cell structure to not only reduce R-on, but also the product of R-on and QGD. So our qualification procedure, so I'm turning back to goal 1, which is to qualify the process. Our qualification procedure was to design and make a mask set for manufacturing silicon carbide power MOSFETs, so we're qualifying those. We're also qualifying a process for JBS FETs, and then we're qualifying a process for JBS rectifiers. Then we wanted to run at least 3 lots. I should say we decided to run 3 lots with the same mask set and process, which are staggered, so that we can then compare the performance between these lots, confirm that we have very good parametric distribution within each lot from wafer to wafer, and then from lot to lot. In order to take the statistical data, we have just acquired some equipment, a semi-automated Signatone wafer prober with 6-inch capability. It has the capability to test to 3 kV and up to 300 degrees C. And we have purchased a Keysight test equipment set that can measure up to 3 kV at 20 amperes. And this has all been installed and is now operational at CSU. In terms of the designs, we have designed power MOSFETs as shown in the middle, JBS FETs as shown on the left-hand side, and JBS rectifiers on the right-hand side. So there are 3 MOSFETs in our design, 3 JBS FETs, 2 JBS diodes, 1 PIN diode as a reference. And we are using the hybrid JTE termination because, as found in BP1, that gives us the best breakdown performance. The mask set and process was reviewed in detail by X-FAB. Unfortunately, we have had a problem with wafer supply. This is universally a problem, I guess, at X-FAB in terms of starting lots. So our wafer lots have been delayed by 3 months plus. We are told that the wafers should arrive by January 30th. I have not heard whether they actually arrived. We are on the 1st now, and hopefully they will start our wafer lots. I want to quickly mention what this hybrid JTE termination looks like. This is the one that we found gives us excellent performance. It is a marriage between the MFZ JTE termination and what is called ring-assisted JTE. So on the lower part of the graph, there are lines indicating performance of various types of terminations. The single zone JTE is a very old one. It's shown by the blue line, and you can see that it's very sharply peaked, meaning that you have to have a very precise JTE dose to make this work. If you deviate from that zone, then the performance degrades rapidly. If you use the MFZ JTE shown by the black line, it works very well at higher doses. And then if you look at the RA JTE shown by the red line, it works well at lower doses. So by marrying the two, you get the, I guess I could call it the hybrid JTE orange line, and that is very broad in terms of process tolerance. So that is the one we are using in our designs. Okay, so as I said, those wafers have not run because of wafer supply. So instead, while waiting for them to run, we took the BP1 wafers and started doing some statistical measurements. These measurements were taken by hand by my student on individual die before we installed our automated probe station. So this is taken very tediously, but at least we have a sampling of about 50 sites. And you can see that we have sampling 2 types of devices that we have been working on. I already talked about the inversion mode MOSFET. I did not talk about the accumulation mode MOSFET before, so let me briefly introduce that. It is a cross-section below the inversion mode MOSFET, and the difference between the two is that instead of a P-based region, we have an N-based region in the accumulation mode MOSFET. This is still a normally off device or an enhancement mode device with a positive threshold. The difference is that the N- base is used so that we have an accumulation layer for the channel, and we have shown in the past that that will give us better mobility. So that is confirmed in the devices that were made in BP1. So on the lower side of the slide, on the left-hand side is the threshold voltage. The red bar charts are for inversion mode MOSFETs, and the threshold voltage is fairly tightly distributed around AccuFETs, accumulation mode FETs. The threshold voltage is about 2.2 volts, and again, if you look at the lower right-hand side, noise is coming in. Okay. Yeah, okay. So on the lower right-hand side, you can see that the channel mobility for the AccuFET, which is the blue part, is substantially greater, almost twice the value for the inversion mode MOSFET. So this is important in terms of reducing RDS on. And in both cases, the mobility is very tightly distributed, which is very good from the process standpoint. We've also measured the MOSFET on resistance, as shown on the lower left-hand side. And again, we find that the distributions are fairly tight. And of course, as expected, the AccuFET has better on resistance than the inversion mode FET because of the better channel mobility. On the lower right-hand side, we have the on voltage of the JBS diode, and that is also very tightly distributed around 2.2 volts. So the preliminary measurements on BP1 wafers already look good. We hope that when we do the all wafers, we will get equally good distributions and a lot more statistical data, which we'll capture using our new setup. In terms of the second task in BP2, to make devices with improved high-frequency figure of merit, our approach is to add a JFET implant, which was not there in the previous design. There's a JFET region, but not an enhanced doping in the BP1 devices. By increasing the JFET doping, we can reduce its width, WJ, in the cross-section. And by doing that, you can reduce the cell pitch. And we have done another attempt to reduce our cell pitch by putting the contact to the P-body orthogonal to the cross-section. So by using these innovations, we can reduce the cell pitch down to 6 microns, which helps reduce RDS(on). And by making the width of the JFET region smaller, we can make the CGD also smaller. So these two allow us to make the figure of merit better as well. So this chart, this slide 30 shows a table where the upper part gives you the performance of the BP1 device, and that had a W cell of 5.5 microns, and the predicted breakdown voltage was about 1400 volts. The QGD was 355. Now these are simulation results, so we give them in nanocoulombs per centimeter squared. RDS(on) was 6.75 milliohm centimeter squared. So when you take the product, we get a figure of merit of about 2400 milliohm nanocoulombs, which is picoseconds. So we use that as a reference, so I'll call that improvement as 1.00. In BP2, our design has a cell pitch of 2.8 microns because of the innovations I just described. Our predicted breakdown voltage is much better for the cell, 1600 volts, and it will be then limited by the edge termination. QGD shrinks to 233, and R(on) improves to 3.47. As a result, our figure of merit is greatly improved to 809, or an improvement by almost 3x. Now, to put this in context, we looked at products available from various sources. The three are shown here: Cree, STM, and Robe. All of these are 1.2 kV devices. There is considerable variation in the product of QGD and R(on) among these different manufacturers, showing that there are different cell designs, processes, etc., being done in the industry. But they generally fall around 2,000. Some are better, some are worse. So in comparison, we've given you the values for the improvement on the right-hand side. And what we find is that our BP2 design is better than all these commercially available devices. I'm sure they're also doing innovations and working on improvements. So by the time we make our devices, there may be a part that is approaching our design, but right now, our design looks pretty good. Okay, in terms of fabricating, we did proceed to make these devices. These are the devices that were delayed, were the qual lots, but we did start one lot with available wafers to make 1.2 kV MOSFETs with improved figure of merit. This took about 19 weeks, so it's a fairly long time frame, but the devices came through on January 23rd, allowing us to start getting. So I want to share with you the results on these devices as measured in the last week or so. So for the MOSFETs, for the inversion channel devices, we found that even devices with a channel length of 0.3 microns work very well, and we were able to get an RDS(on) of 6.7 milliohm centimeter squared at 10 amps with a VG of 20 volts compared to 25 volts in the BP1 designs. And the threshold voltage was 3.15 volts. So these look very good. On the right-hand side, we show you the blocking characteristics of the inversion mode device in green, and you can see that it's excellent with the hybrid JT termination with very low leakage current and a breakdown voltage of 1700 volts. So this is looking very good in spite of a channel length of 0.3 microns. The performance of the AccuFETs is satisfactory in terms of the spec, but is not as good as the inversion mode device in terms of leakage. So here's the results on the AccuFET. In this case, we are showing you the results for a channel length of 0.5 microns. Because of the improved mobility, the RDS(on) is very low, 6.3 milliohm centimeter squared at 10 amps with a VG of 20 volts. The breakdown voltage, as shown by the blue line on the right-hand side, that is the BP2 AccuFET with hybrid JTE. You can see that the breakdown voltage is 1600 volts. The leakage current is higher than for the inversion mode device, but I think it's still satisfactory. So our major accomplishments in this task are that we've successfully done all the mass designs and process definition on schedule. This was scrubbed in detail by X-FAB. It took them about 3 months going back and forth, so but they successfully then started the wafer and delivered the wafers to us. Unfortunately, there was one problem. Let me see what I have here coming up. Yeah, so let me finish this chart. So this says that we accomplished our goal in terms of making the high-frequency figure of merit devices in 19 weeks. Unfortunately, only the wafers without the JFET implant worked, and of course, the JFET implant was the innovation in our process. So we did some investigation, and we found that there was an error in processing these wafers, and aluminum was implanted instead of nitrogen. As a consequence, the devices did not work. So those wafers are now being rerun, and we hope to have results in the future. So that is a quick rundown of the status and the plans for BP2. And again, in summary, in our project, we're working towards developing an open domain process to make MOSFETs, JBS FETs, and JBS rectifiers. And we're also working on trying to create some innovative devices that will hopefully accelerate the introduction of silicon carbide devices into the industry, like the JBS FETs, and also devices with better high-frequency figure of merit for competing with IGBTs. Thank you for your attention.
Thank you very much, Dr. Balaga. Very information-packed presentation. Thank you all for joining us today. We have time for questions and answers. With a large number of folks on the line, though, I would ask that you use the chat function. You'll see a chat button in the upper right-hand corner, and if you type in your question, I'll read them out so everyone can hear the questions and the answers. Okay, I'm not seeing any questions. Okay, the first question is, what is the process used to simultaneously obtain Schottky contact, ohmic source contact, and ohmic body contact?
Okay, I'm going to answer your question, but I'll use a cross-section to help me do that. So if you look at the slide I put up now, slide 28, you can see that there is a Schottky contact made in the N-type drift region on the left-hand side in the JBS FET. And at the same time, we have to make an ohmic contact to the P body region. So to achieve this, we would prefer to use a single metal and anneal process, because if we don't, then you have to use much bigger dimensions, and the process gets more complicated. So we did some work in BP1, and we have published this. It shows that by using nickel as a contact and annealing it at the right temperature, which you will find in our papers, we are able to make good Schottky contacts with low leakage current and proper barrier height, and also make simultaneously an ohmic contact to the body. But to achieve the ohmic contact, we have to increase the doping of the body. So there is a P plus region, so we call it the P plus ohmic in our slide. There is an enhanced doping done in that region. So we have successfully developed this process to greatly simplify how to make these devices with the metallization that we are using.
Thanks. Are there any more questions? Second question, are you using an aligned channel? And how do you compare this to a self-aligned channel process?
Okay, so in our process at X-FAB, we do not use self-aligned processes. So the N plus and P body are implanted using two separate masks, and the alignment is based on the alignment tolerance at X-FAB. So this is why we are now examining the statistical distribution of all our parameters to see how that impacts the distribution, because the channel length is going to vary from die to die and wafer to wafer.
Okay, the next question is, are you using or did you use a different oxidation for ACC and inversion MOSFET?
No, the oxide process is the same for both devices, but the channel construction is different because the inversion mode device has a P-type base, and the accumulation channel has an N-type base. But the oxide is formed with the same process.
Okay, the next question is one that I'm sure a lot of people are feeling. There's a lack of silicon carbide wafers. What supplier is X-FAB using, and will this situation change in the future?
I'm sorry, that's a question you have to address to X-FAB. I'm not privy to the answer.
Okay. Are there any more questions? What are the next steps in the project?
Okay, so I sort of outlined them. Unfortunately, we had an error in processing our high-frequency figure of merit lot, so that is being repeated. It'll take, again, 19 weeks, so that's one of the things that's being done. We are told the wafer should arrive or hopefully have arrived. So then we will start our qual lots. So that's the next step, but that'll take, again, at least 4 months, after which we will get statistical distributions on those devices. So a lot of our work is predicated on X-FAB completing the fabrication based on the work we have done in terms of design and process definition.
Okay, the next question is, what are the plans for HTGB for any reliability testing?
So the question is, what kind of device reliability testing? I would say in general, HTGB is a device reliability test. So I want to clarify again, we are not qualifying devices. We are only qualifying a process. By that I mean how tight is the distribution of parameters on wafers, and how well does the process yield a particular type of device. Any person on any company or member that wants to use this process would have to make their devices with their designs and then qualify their design independently. So again, I want to be very clear that we are not qualifying devices. We're only qualifying a process, which will become hopefully a foundry process for your use.
Right. Similar question. Will you be packaging and deploying these devices?
These devices are not going to become commercially deployed. If I use that word, I'm thinking commercial. We are a university program. We have packaged some devices for testing purposes, and we are going to package especially the JBS FETs because we have colleagues who want to put them into circuits and show that they will work better than having separate MOSFETs and diodes. So that is certainly in our plan, but it's all for demonstrating performance at the university level. And if the results look compelling, I'm sure a lot of companies will then start producing products.
Thank you. Is the new Keysight tester system up and running 100%?
The answer is 95% maybe. Nothing is ever 100%. So it took a while in January to remove all the bugs, and we also put in some safety features in order to be sure that the students are well protected during the testing, and those safety measures were sometimes malfunctioning. So fortunately, Signatone has worked with us, and Keysight has also worked with us to iron out all those issues. We have not yet done the wafer level characterization to get the statistics, so I'm keeping my fingers crossed that everything is now in place and it should go smoothly. But we have not actually done one run for wafer level statistical data gathering. So that's why I said 90% perhaps.
You said 95.
95, all right.
Keeping count.
I could raise it to 90.
Okay, will there be any costing of the process and cost benchmarking?
That's something that Power America would have to do. So I would leave it to the management at Power America. I think first thing we have to do is to show that we have a good enough process that's worth costing. So I believe that we should first finish the qualification that I talked about. I'm fairly confident that it will look good because I have great confidence in X-FAB's ability in terms of processing. So once that's done, or in parallel, we should probably try to figure out some sort of a costing as well. But I would send those requests to the management of Power America. Not to me.
Okay, the next question, is there any gas purge onto the wafer surface during testing?
We do not use any purging in our tester, and to our satisfaction, I should say, to my particular satisfaction, we found we could test to 1700 volts without any problem. And I like that a lot because it simplifies the setup and gives us the ability to do tests to get these breakdowns. I should mention that the 3.3 kV and 4.5 kV tests were done in, it's not coming to me, in that liquid.
Fluorinert?
Fluorinert, thank you. Yeah, Fluorinert. So those higher voltages require that we put Fluorinert. So they were done in a separate test fixture that we have that can go up to 15 to 20 kV actually. It is not the Signatone test setup.
What about over temperature capabilities?
So our test setup can go up to 300 degrees C, as mentioned before. So we plan to exercise that again. That's a new feature, and right now we're doing calibrations to make sure that the chuck temperature matches what is read out by the controller. And once we have done all that calibration, we will also do high temperature measurements.
Someone asked how cold?
Oh, cold. We do not have the ability to go cold. So this will be room temperature and above.
And someone else joked that they also recorded that you quoted a figure of 95%.
Okay.
Previous slide.
Yes.
Someone that we know.
That's fine. 95%. I'll accept that. Yes, fine.
Are there any more questions? You're welcome. Well, thank you all very, very much for joining us today. I think this is the largest turnout we've gotten for any of our webinars. And if there are no more questions, I think we'll end it right here. As I said, we do this on the first Wednesday of every month at noon. The next webinar will be Wednesday, March 1st, and that'll be given by our Dr. Douglas Hopkins from here at NC State. Okay, goodbye, everyone. Thank you all for joining us.
How many do we have?
I want that in writing.